Welcome, everyone, to today's episode of Science Uncovered. Today, we're diving into the fascinating world of catalysis, specifically a groundbreaking technique called dynamic catalysis. I'm your host, Joanna, and I'm thrilled to be joined by two experts in the field, Matthew and Kimberly.
Thanks for having me, Joanna. It's great to be here.
Absolutely. Excited to discuss this important work.
Wonderful. So, for our listeners who may not be familiar, can we start with a basic explanation of what catalysis is and why it's so vital?
Certainly. Catalysis is essentially the process of speeding up chemical reactions using a substance called a catalyst. This catalyst doesn't get consumed in the reaction itself but facilitates the transformation of reactants into products. Catalysts are incredibly important, because without them many industrial chemical processes would be far too slow or energy-intensive to be practical. Think about everything from making plastics, fertilizers, and pharmaceuticals, to even refining oil for fuel. Catalysts are crucial to all of that.
And, let's add that catalysts are also increasingly critical for creating cleaner and more efficient energy production technologies. Catalysis plays a massive role in reducing emissions, optimizing efficiency, and generally making manufacturing processes much more sustainable.
That's a great point, Kimberly. So, what's the limitation of the traditional catalysis, and how does dynamic catalysis offer a solution?
Traditional catalysis relies on static catalysts, meaning, their properties stay fixed. There's a principle called the Sabatier principle, which basically states that there's an optimal level of how strongly a catalyst binds to the reactants. Too weak, and the reaction is slow; too strong, and the products stick to the catalyst, hindering the process. It's like finding that sweet spot in a reaction. This sweet spot is where the catalyst is able to maximally produce the needed product.
Exactly. Dynamic catalysis tackles this limitation by periodically changing the binding strength between the catalyst and the reactants. It's like giving the catalyst a tiny push and pull rhythmically, enhancing the overall effectiveness of the whole process.
So, it's not just finding the sweet spot but making the catalyst repeatedly visit that sweet spot during the course of a reaction, maximizing product yield. This paper explores a novel way to simulate this dynamic behavior, doesn't it?
Yes, precisely. The researchers used a modeling language called Pyomo and a solver called adsorbate to create a far more efficient way to simulate these complex dynamic systems. Traditionally, these simulations required extensive computing power and time. The new approach is orders of magnitude faster and more efficient.
This efficiency is due to their novel approach of focusing on cyclic steady states, avoiding the need to simulate the entire process from start to finish. It's akin to knowing the outcome of a process after a specific number of cycles, thus shortening the simulation significantly. This increased efficiency enables scientists to explore a wider range of parameters and catalyst designs, leading to a much more comprehensive understanding of how to optimize these reactions.
That's incredibly insightful. Their results seem to show that dynamic catalysis can push reaction rates beyond what was previously thought possible, surpassing the limitations of traditional catalysis, right?
Correct. The researchers visualized this using something called an extended Sabatier volcano, a graphical representation showing how the modulated binding strength significantly improves the rate of reaction. They essentially found optimal patterns of modulation that lead to substantial increases in the overall productivity of a reaction.
And the really exciting part is the potential applications. This isn't just theoretical. The enhanced efficiency and sustainability offered by dynamic catalysis could revolutionize various industries, from chemical manufacturing and energy production to the development of new materials and medicines.
That's truly remarkable. So, to wrap things up, what are the key takeaways from this research?
Dynamic catalysis is a promising way to improve catalyst performance. The new simulation methods provide an incredibly efficient means to study and optimize this dynamic behavior. The results demonstrate that carefully designed modulation patterns can significantly enhance reaction rates beyond traditional limits.
Exactly. And that this improvement has wide-reaching implications for creating more sustainable and efficient chemical processes, especially in the energy sector. It really opens doors to better, more sustainable solutions for numerous industrial challenges.
That's fascinating. Thank you both, Matthew and Kimberly, for sharing your expertise on this groundbreaking research. To our listeners, I hope this episode has shed light on the exciting possibilities of dynamic catalysis and its potential to reshape the future of chemistry and beyond. Join us next time for another exciting adventure into the world of science.